My name is Adam, and my teammates are Mary Grace McGinnis and Wilson Tran. We are Team 2, Section 2 in Penn State's ME 435 Systems Lab. Over the last few weeks, our team has worked with a small autonomous robot called the JetBot. We completed 3 different labs to build our understanding of the JetBot. Lab 1, which focused on basic robot control and kinematics, Lab 2, which covered path following and sign recognition, and Lab 3, which focused on localization and path planning. Through these labs, we've implemented the knowledge we gained to complete our final project, where the goal was to have the robot autonomously navigate the course while following the road and making decisions based on its environment.
In Lab 1, we focused on learning the JetBot programming system and using kinematics on the robot. The JetBot runs a Python-based coding system called the Jupyter Lab. Then we were tasked with directing the robot to move forward, make a 90-degree left turn, continue moving forward, and then stopping at a set point on the track. To do this, we tested the speed of the robot and used basic motor control and timing to complete this task, along with redundant experiments.
In Lab 2, we focused on building a path-following control system for the robot, using its camera as a sensor. The first step was image processing. We converted the image from RGB to hue saturation value, or HSV color space, and adjusted the HSV boundaries. By tuning these values, we were able to isolate the yellow line on the track. We then calculated the heading angle by finding the angle between the center vertical line and the average position on the yellow line. Using this heading angle as an input, we implemented a PD controller to generate signals for the motor wheels. We tuned the PD parameters until the robot followed the path smoothly. In the same lab, we trained sign recognition model using the robot's camera. We collected about 40 images for each category, one for no signs, stop signs, and speed signs, respectively. To make the dataset more reliable, we moved the robot to different locations and different angles each time to vary the backgrounds. After collecting this data, we trained the model for several epochs. Once training was complete, we tested the model by placing the robot in front of each condition. Prediction sliders showed the probability of each category, and we could see if the model correctly identified signs or the lack of signs.
In Lab 3, our team demonstrated an understanding of basic networking to exchange information between our computer and multiple JetBots to operate with them interactively. We started with networking where the JetBot communicated with a second robot called the CameraBot. The JetBot sent a command to the CameraBot to capture an image of the road map, and that image was then sent back to the JetBot for processing. After that, we performed camera calibration on the CameraBot. This step was necessary because the image has distortion, especially near the edges. Calibrating the camera allowed us to correct that distortion so the position calculations would be accurate. Next, we moved on to April tag detection. Using the camera's image, the system detected an April tag on the JetBot and calculated the robot's position and orientation on the road map. Once April tag detection was working, we implemented real-time location detection. Instead of calculating the robot's position at once, the robot continuously updated its X and Y position while it was running. With the robot's location known, we then focused on path planning. First, the road map image was converted into a black and white map, where white areas represent drivable space and the black represented obstacles where it could not drive. The program then generated a set of possible routes across the open areas of the map. Using the robot's current position as the starting point, the program searched through those routes to find the shortest path to the target location. The final path was highlighted in red. This represents the route that the robot would follow from its current position that we defined to the goal while staying on the road.
To begin our fourth and final lab, we were tasked with creating a flowchart of a program that would enable our JetBot to travel autonomously from location 1 to 2 using the shortest distance while following roads and traffic signs. To do this, we created a flowchart featuring all 5 systems that we learned in the previous labs. The features that we included were kinematics, sign recognition, path following, robot-to-robot communication using April tag and path planning. To begin the process of the flowchart, we start on the left. Then we input the camera bot live feed, then we input 3 different things at the same time. First, the conversion, which makes the pixels to scale. Then we input the JPEG map that we have, which is converted to scale. And lastly, the JetBot's current pose and the goal location of the JetBot. All of this information is then used to determine the best path for the JetBot to follow from location 1 to location 2. Then the JetBot would connect to the camera bot using the April tag. Then the program would verify the nodes in the relationship to the program, which is essentially verifying the planned path. Then on top of the flowchart, we see the input of the JetBot's live camera, which feeds into both the path following code and the sign recognition model. The path following directly ties to the kinematics of the path that the JetBot will be following, which flows in the sign recognition, which enables the kinematics of the sign recognition model until the next node is reached. And once reached, the verifying of the location of the node will occur. This causes the kinematic system to move on to the next node until the final node is reached. The JetBot at the final node will end the code.
For our final project, we brought together everything we learned from labs 1 through 3 to create a robot that could follow lines, recognize signs, and be tracked by an overhead camera. This project was a culmination of our work, showing how kinematics, control, and networking can all come together. We started with our path following code from lab 2, then added the sign recognition code to it later on. We had the robot check for signs about every 3 seconds, so we didn't overload the JetBot's processors.
We implemented real-time location detection code from Lab 3 into our final code. The code couldn't be completely taken from the lab, as we did have to change the time variable to a different name so the variable was not overwritten. Time was defined earlier in the code, which was interfering with the camera on the robot. After changing the name, the robot ran smoothly and the location was displayed.
Overall, our final project showed how the core ideas from labs 1 through 3 could be combined into one project. We built a robot that could follow lines, recognize signs, and be tracked from above using April tags. In the end, this experience reflects what we value most here at Penn State: learning by doing. We're proud of what we built, and even prouder to say that we built it here at Penn State.